x plus 2 is 5. What's x? And you can write down your numbers there. Remember that I won't be able to take the volume back. But I'd say a lot of you here will be able to do that. Okay? What you would probably say is that x is 3. But let me show you a technique that I would use on this. I would say I would like x to be on the left-hand side on its own without the 2. So I'm going to say x plus 2 is 5. The plus 2 I don't like, but there are pairs of operators in mathematics, and what's the pair that goes with addition? They talk about addition and subtraction. Is that okay? So if I take minus 2 here on this side, I can take minus 2 on that side. They would cancel, and I'd be left with x equals 5 minus 2. And they're both on the same side, both numbers, x is 3. Is that okay? Nothing too ear-chattering there. You then went on in primary school, following addition, to do subtraction. Y minus 3 is 8. What's y? You'd say 11. But another way of doing it is y minus 3 equals 8, leaving a space. What's the twin of minus? Plus. If we do it on this side, we must do it on this side. So y becomes 8 plus 3, which is 11. So that's something you did in early primary. You then went from early primary into middle primary, and you did multiplication. 3x is 12. What's x? 4. But another way of saying it is, I don't like 3 here. It's a multiplier. The pairing of it is a divider. So I'm going to divide. X is 12 over 3, which is 4. And pretty much at the same time, or maybe the following year, you did division. Y over 5 is 10. What's y? Well, this is division. What's the opposite of division? Multiplication. So if I put in a 5 here, I must do a 5 here. Like if, one Big Mac is a 5er, 2 of them is a 10er. Whatever you do on one side, you do on the other. They cancel. Y is equal to 50. Then, towards the end of primary, you were doing things like squares. So you had a thing like x squared. X squared was 9. What's x? Now, what's the pairing of squared? What's the opposite of squared? Square root. So what you do is you say, if I took the square root of this, I could take the square root of that. And really, the square root of x squared, I don't really have to know what it is, because I know it's the opposite. What I know is, it sort of gets rid of it, and it just leaves me with the x. And the square root of 9 is, what's the square root of 9? 3. Sometimes plus and sometimes minus 3. Okay? Because minus by minus is plus as well. Is that okay? And again, towards the end of primary, maybe, if a good teacher, you have something like the square root of, the square root of x is equal to 5. What's x? What you say is, you say, I don't like the square root thing. What gets rid of a square root? Well, if I were to square this, and what's the square root of, or the square of a square root? Well, it gets rid of it, doesn't it? I just have x equals 25. So what we're seeing basically are paired operators. Is that okay? Now let's look at it going forward, and we say, what would happen if it was x cubed is 8? What is x? Probably you'd say 2. But maybe you'd say, I don't know. So what I'm going to do is I'm going to take, what's the opposite of the cubes? On your calculator, what's the one that has inverse beside it? The cubic root. So if I write it down again, x cubed is 8, and I take the cubic root, all I know is that's get rid of all of that stuff. That's why I chose it. X is equal to the cubic root of 8. Now, while this looks tricky enough, there's no x here. This is just numbers. And as numbers, it's just a calculator. So 8, cubic root, 2. Is that okay? No variable anymore. Similarly, if somebody said that the cubic root of y is 3, what's y? Well, really you're saying, let's just cube it. This disappears, and y is 3 cubed, which is 27. Okay? Happy enough? Now, you're into secondary now, and you're doing things like other functions, like maybe powers. And they say, okay, x to the power of 5 is 32. What's x? Don't know really. But I do know that if x to the power of 5 is 32, the opposite of the power of 5 is the fifth root. The x to the y. So it's the one that has the inverse of it. So if you have a calculator that says x to the y, the other button that will say beside it is probably y to the x. Or it may say x to the 1 over y, depending on which calculator form you have. Is that okay? And if I take the fifth root of the x to the 5, the only reason I did it was to get rid of it. And again, it's the fifth root. That's on a calculator. 32, fifth root. The answer is 2. Is that okay? Or if somebody says, what's the fourth root of x? Is 64, maybe. That's not a good one. Fourth root of x is 16. Or no. Well, that'll be, yeah, you could do that. Fourth root of x, maybe, let's take a smaller one. Let's say the fourth root of x is 3. What's x? Well, how do you get rid of the fourth root? Put it to the power of 4. They all cancel. X is equal to 3 to the power of 4. 3 by 3 by 3 by 3 is 81. Is that okay? Now, having done that, let's use it for something a bit more interesting. Let's say that somebody told you that the sine of x was 0.5. What's x? Now, what we've done so far is we've said, I'd much prefer on the left-hand side to have x on its own, not to have anything beside it, not to have x plus 2 or 3x or cubic root of x. I just want x there. But I have a sine x. So how do we do that? So if sine x is 0.5, what's the twin or the pairing of sine x? What's the one that you have the second function on for the sine x? Sine to the minus 1, the inverse sine. So what I could do is I could say, well, let's write the same equation out again, sine x, and here equals. So if I took the inverse sine of this, I'd have to take the inverse sine of this. And what would happen? I'd be left with x equals inverse sine of 0.5. Now, these are just numbers. 0.5, inverse sine, x is 30. If you have the degree button on. Is that okay? Equally, if somebody said that the inverse tan of x is equal to 1, what's x? Sorry, the inverse tan, let's pick a different number so it's more equal. Let's say it's 45. Could be any number, but the inverse tan is 45, let's say. I want x on the left-hand side. How do I get rid of this inverse tan stuff? What's its twin? Tan. So what I'm saying is, I leave the tan inverse here, and I say, if I took the tan of all of that, then I'd have to take the tan of all of the other side. And really, why did I take the tan of the inverse tan? Not because it looked awful. Well, it does, but just to get rid of it. So x is tan 45. 45 is a number. Hit tan in the calculator. X is 1. Okay? So what you're seeing there is that what started in primary was a series of sort of twins that we're now, you know, fairly well having a go at. The last set you do, for some reason, they give you powers in the in your leaving certificate. They say 3 to the power of x is 81. What's x? That's not x to the power of 3, but that's 3 to the power of x. I don't know why they do this. They give you the power, but they don't give you its twin. Its twin is log, okay? Which is strange. They don't tell you. But if you're asked in the exam, what is x? What you do is you say, well, let's try 3 to the 1. That's 3. No. 3 squared? No, that's 9. 3 to the 3? That's 27. No, 3 to the 4? Yeah, it's 3 to the 4. So x is 4. In other words, they leave you there guessing. Okay? But the other way of doing it is you actually use a thing called logs. Now, I'll show you this. It's actually very simple. What you do is, instead of having 3 to the x here, you take the log of it on both sides, log, and you take log here of 81. Now, the great thing about logs is that if you've got something from 3 to the power, logs were designed to make things easy. They take powers and they turn it into multiplication. So the x comes down and you get x log 3. That is the same. The log of 3 to the x is x log 3. And that's equal to log of 81. This is just a multiplier now. That's just a number. That's just a number. So x becomes log 81 over log 3. And if you do that in your calculator, you find the answer is 4. So in one step, you're not guessing anymore. Log 81 divided by log 3 is 4. You don't have to guess them anymore. Now, sometimes they're not that easy to guess. For example, let's say that somebody said, what is that 25 to the power of x is 125. What's x? You'd say, that's a bit tricky. 25 to the 1 is 25. 25 to the 2 is 625. What's this? And in your head, they'd expect you to say, well, 25 to the x is really 5 squared to the x, which is really 5 to the 2x. 125 is basically 5 to the 5 to the 5, which is 5 to the 3. 2x is 3. X is 1.5. Basically, the answer is x is 1.5. So 25 to the x is 125 when x is 1.5. Now, you're meant to know that and spot that in your head. I find that tricky enough. I find that subtle enough. Okay? What I would do instead is I would say 25 to the x is 125. What is the twin of when you have the x in the power? Well, the machine that kills that is log. Log. What's the great one trick about logs? If you've got log of something to the power, it's the same as x times the log of the something. That's a number. That's a number. X is log 125 over log 25. And that turns out to be 1.5. Every time. If you get a power like that in the question, you can't see it, log kills it. Okay? It's in the notes there. The last pair that they give you on the course is they give you a thing called differentiation. They say that if you have y equals x squared, dy dx, they say is 2x. If y is equal to x cubed, dy dx is x cubed over 3. And if y is equal to x to the 4, dy dx is x to the... Sorry, where am I going? Do that slowly. I'm running two things in my head. Y is equal to x squared, and you know that fellas can't multitask, or so they say, so sorry about that. Okay, y is equal to x squared. What's dy dx? 2x. When y is equal to x cubed, what's dy dx? 3x squared, isn't it? And when y is equal to x to the 4, what's dy dx? 4x cubed. Is that okay? So what they have told you is that there is a process called differentiation that takes a number with the power, that takes that 2, uses it here as a multiplication, and reduces this number by 1. So this becomes 2 minus 1. Again, this number here, it takes the number on the top, makes it multiplication, and what does it do here? Makes that 3 minus 1, takes 1 from it. This one here, multiplication, and this one here, 4 minus 1. Is that okay? Now, I don't know why they give you that without mentioning there's a way back. The opposite of differentiation is a thing called integration. That's the twin. Look and see what integration does. Well, what happened in differentiation? You used the number on the top as a multiplier. What's the opposite of multiplication? Division. So in integration, if you had something like x squared, you'd use this number as in some way you'd start thinking about division. And what about this 2 minus 1 thing? You see the way you took something from it? What would you do? What's the opposite of subtraction? Addition. So if you integrate x squared, instead of subtracting from 2, you'd add to 2. So you'd call it x cubed. And instead of using it as multiplication, you'd actually divide. Instead of x cubed, you'd take 1 above it, 4, and divide by 4. Now, let's see if we did it on the way back. Let's say if we differentiated here. What would happen if we differentiated x cubed? What would we get? 3x squared. And then if we divided the 3x squared by 3, what would we get? just 1x squared, wouldn't we? What would happen if we differentiated x to the 4? 4x cubed. And we divided the 4x cubed by 4. We'd end up with x cubed. Is that okay? And they actually, when they do it, they also say, well, they put in a constant here, a thing called a plus c. Because if it was x cubed over 3 plus 2, or x cubed over 3 plus 17, or x cubed over 3 plus 9, and you differentiate it, what happens when you differentiate a constant? It goes away. But that's what integration is. Okay? And it just means that there's always a way back. And that's all it is. It's nothing more than that. It's just the things that came up, and there's a pattern and a way back. Now, what we're going to do is we're going to start using some of those skills to manipulate equations. We won't go through this in too much detail, because really it's all about, it's like Sudoku. You know the way you get one square and you move around and you get another one? Or you do Venn diagrams, you find a bit and you go around in a puzzle. Manipulating equations are exactly like this. So I'm going to do some of them, but you can do more. They're all on the video anyway from other sessions. Is that okay? So there's nothing I'm going to leave out conceptually. A over B equals C over D. Remember I started with, I liked x on the left-hand side. So imagine if somebody says, what's A? I don't want A over B, I just want A. What would the answer be if it was just A here? Well, I could look at the left-hand side, and do I like the left-hand side? Is there anything I don't like? Well, I'm not gone on the B. What is the B? It's dividing, isn't it? And how do you get rid of division? Multiply. So what you do is you say multiply this by B, multiply this by B. If I multiply this by B, they cancel. That's why you did it. So A becomes BC over D. Is that okay? And that's all the equations are like that. A over B plus C over D equals E. Fairly messy equation like that. What's D in terms of the others? So imagine if somebody said, there's an equation. A over B plus C over D is E. And I just want D to be on the left-hand side on its own. So will you give that a go? Anything you don't like, get rid of it. Put it on the other side. It's a multiplication, divide it. If it's a divisor, multiply it. Just give that a go for a minute or two. Okay, I'm going to give that a go. I'm going to look at the letter D here. We could pick any one of these as our interest point. But let's imagine that they've asked us to look at D as our point of interest. So my focus is getting rid of everything but D there. Well, the first thing I'm not going on is that, well, maybe I'll write it out again and start from the beginning. So A over B plus C over D is E. Well, at least D is on the left-hand side. That's not bad. I don't like this A over B, but. So I'm going to say A over B minus A over B plus C over D is E minus A over B. Effectively, what I've done is I've subtracted this on this side and the same on the other side. Okay? And that cancels that. So I'm now left with C over D is equal to E minus A over B. The D is on this side, but it's not really a great spot, is it? It's sort of on the bottom, isn't it? How could I get rid of it on the bottom? What's it doing on the bottom? Dividing, isn't it? So if I were to multiply it, let's see what would happen. If I were to multiply it here, I'd have to multiply on both sides. And now I'd be left with C is equal to D times E minus A over B. That's not great, but at least it's on the top. You've got to look positive about it. It's also on the wrong side again. But anyway, okay. It's on the wrong side and it's on the top. It's on the top. What, is that a multiplication there? Times that? So if I were to just take that lump, E minus A over B, and divide on this side E minus A over B, that would all go. So the next time I'd be doing this, I'd be a lot further on in that really I'd have C over E minus A over B is D. And really I could just swap that. I could say if D is equal to it this way, it's equal to it this way. C over E minus A over B. I could do it that way. Or let's say I really don't like it on the right hand side. If I was going the slow way, okay. So we don't have, this doesn't need to be pretty now. The fact that E minus A over B is ugly doesn't matter. Just imagine that that's the number 3. So we start here and we say, what we started here by saying D times that. So D times, the C was equal to that. So we had C was equal to D, E minus A over B. So imagine that was just C is D times 4. C is 4D. Well, you divide by 4 on both sides. I'm just taking this and I'm dividing it by E minus A over B and dividing it by E minus A over B. And they will cancel. Just if that was 4D and divided by 4, I'd just be left with the D. That's the mess I have. So what I have now on the top is I've got this mess here. How do I get rid of this? How do I get D back? Well, D is on the wrong side. So how could I get rid of the D on that side? Could I subtract it? So what I'm going to do is I'm going to say C over E minus A over B is equal to D. I could say D minus D here. And that would go to 0. Now I could take this over, I could get rid of that C bit. C over E minus A over B minus C over E minus A over B minus D is equal to nothing minus C over E minus A over B. Minus D is equal to minus C over E minus A over B. If I multiply both sides by plus or by minus, I'd get the same thing. So there's a whole load of ways of going around that loop. Let's do something that's maybe immediately more in tune with you. In your formula tables, they give you a whole set of formulas for stuff, don't they? Surface of a sphere, series and sequences, a whole lot of things. But they only give them to you in one way. So just imagine they gave you this equation for the volume of a sphere. V is equal to 4 over 3 pi r cubed. It's possible, in the leaving cert, they might say, calculate the volume of a sphere given the radius. It's far more likely that they'll say, look, this is the volume, what's the radius? The volume is 10,000, how do you work out the radius? In other words, what they're saying is that the focus of interest is in R, not in V. So how do you figure that one out? You'd like R on the other side, wouldn't you? Well, you could swap things around, but let's start by saying, how do we simplify that? V equals 4 over 3 pi r cubed. Or, taking it over to the other side, we could say 4 over 3 pi r cubed is V. R is on the right side for us now. That's good. But it's covered with a whole lot of mess here, isn't it? What's the 3 doing there? Is that dividing? How do we get rid of it? Multiply. So 3 times this would be 3 times that. They'd cancel. We'd get 4 pi r cubed is 3v. Is it a bit better? Yeah. What's 4 pi? Is 4 a number? Pi a number? 4 pi is like about 12 or something. So that's just a number. Is it a multiplying? How do I get rid of multiplication? Divide. So if I divided both sides by 4 pi, what would happen? They'd go, wouldn't they? So I get r cubed is 3v over 4 pi. We're making progress. We've got r cubed is 3v over 4 pi. But what am I interested in on this side? What would I like that to be? Just r. And how do I get rid of a cube? Cubic root. So r is basically the cubic root of 3v over 4 pi. What do they give you in the exam? They've told you that the volume is 10,000. That's a number. 3 is a number. 4 is a number. Pi is a number. 1, 2, 3, 4. Cubic root, you have your r. Is that okay? You get the idea? It's just a merry-go-round. That's what algebra is. We do one more like that. The volume, I think, of a cone is given as V is equal to 1/3 pi r squared h. It's possible they'd ask you to work that out. By the way, both of these are in the notes. They're both just on a little bit. They're on in your notes on, well, that one there was. It's called rearranging equations, so it's following there. But let's go through it anyway. Let's imagine that our focus of interest this time is h. I'd like h to be on the other side. So you can always change the sides. So you can say 1 over 3 pi r squared h is v. H is on the right side for me. Don't like the third here. So I'm going to multiply that by 3. They cancel. So pi r squared h is 3v. Not got on the pi really here. So I think I'm going to divide by the pi. So I get r squared h is equal to 3v over pi. In fact, not particularly gone on the r squared either. So h, well, I'm going to divide by the r squared, and I'm going to get h is equal to 3v over pi over r squared. Well, let me do that right, so we're not confused, okay? It's pi r squared h is equal to 3v. That's multiplication here. So I could actually say, well, I'm going to divide that by pi, and I'm going to divide that by pi. R squared is also multiplication. I could divide that as well at the same time or later, but let's do it just later. R squared h is 3v over pi. Now, h is equal to all of this, because what I'm going to do now is I'm going to divide by r squared, divide by r squared, and I'm going to get h is equal to 3v over pi all over r squared, or 3v over pi r squared on the calculator, because I'm dividing the 3v by pi and again by r squared. And that's my equation. You are going to have these in the exam. They are going to give you something to turn around. You know, they won't give it everything on the left-hand side and say, please just plug in numbers. Is that okay? And you have to be able to do that. Just one thing while we're at it. A number of you will be familiar with this one here. A over b is c over d. And how do you solve that? A number of you would be using this crisscross method. So you'd say a over b is c over d. How do I solve this? And a lot of you would say that times that is that times that. You'd say a times d is c times b. A over b is c over d. A lot of you would do the crisscross method. The thing on the top here, a, by the thing on the bottom here, d, is equal to the top here, c, by the bottom there, b. And that's how you would normally do that. But what did I do? I said a over b is c over d. And I said, I don't like the b on the bottom, so I'm going to multiply by b. And that's going to give me a here is bc over d. And then I said, I'm not really gone on the d on the bottom here, so I'm going to multiply here by, I'm going to multiply this by d and multiply this by d. I get AD is BC. AD, BC, or AD is CB. It's the same thing. 3 times 2 is 2 times 3. So I was just taking it in 2 steps rather than in 1 step. Is that okay? So there's nothing you can't do. Think about the only things they've told us, really, are addition, subtraction, multiplication, division, powers, or sort of roots and cubed roots and stuff. Then there's the powers, and I would suggest the logs, the inverse tans and the tans, and that's all that can come up. So all you have to do is say, take one at a time, unpick it, like you would a Sudoku quiz, and it's done. Is that okay? Step by step until you get what you want on the left-hand side. Everything else will be given to you. All the other numbers will be in the question. You just have to put the thing you want on the left-hand side. Is that okay? So here's a typical now. So that's what they would do. When you've done that, there's another section in algebra called just plugging in numbers, really. And it says, evaluate p squared plus 4q over this when p is 1 and q is 2. So just do that. Plug in those numbers there. Okay, I'll plug in the answers there. What you do is you almost sort of go into lockdown mode. And you say, you know, P is 1, Q is 2. You put your little table beside the question, sort of the side work. P is 1, oh, that must be P squared would be 1 squared. For Q, what's Q again? Oh, that's 2. On the bottom, 2 times Q, what's Q? 2. Plus, that's within the brackets, plus 1. Okay, 1 squared now you do is 1, plus 4 times 2 is 8. In 2 times, 2 plus 1. Inside the brackets you do 3. So that's 9 over 6, which is 1.5. You'd wonder why, really, they give you these questions. How could people get different answers? How could people make mistakes? Well, people do. Because there's a convention out there called PEMDAS, or sometimes called PEMDAS, or in the States they call it PEMDAS, where they say brackets come first, then you've got these, you know, components, their ofs or their powers or their indices, multiplication, division, addition, subtraction. In America, they call it parentheses for brackets. Exponents, it's the same thing. We're talking about powers here. Powers or ofs or whatever, right? Orders, all the way through. In America, they call that, please excuse my dear Aunt Sally, which is pretty awful. But that's what a high school person in the States would have to suffer. Please excuse my dear Aunt Sally, in that order. But why do they do that? What they're saying is that if you take a set of numbers like this, and I ask you to calculate them. 3 plus 4 times 2 minus 7 by 2 minus 1. Or maybe I'll leave it without that there. I'll just say 3 plus 4 by 2 minus 7 by 2 minus 1. You might ask somebody to calculate that for you, and this is the actual question. But you might interpret that. This is you, interpretation. Maybe through sort of commas or voices or something. This is interpretation 1, interpretation 2. Or maybe I'll just call them 1 and 2 so they're not confused with the numbers. You might have thought the first one is 3 plus 4 by 2 minus 7 by 2 minus 1. But there were sort of brackets here. Brackets there. Or this might have been, somebody else could interpret it as 3 plus 4 by 2 minus 7 by 2 minus 1. And we'd all get different answers. The question really is, what is 3 plus 4 by 2 minus 7 by 2 minus 1? And if you're using a calculator to do all of that in one go, you really have to be extraordinarily careful, because it's very easy to get the wrong answer. What this is really saying is that 3 plus 4 you might think is 7, by 2 is 14, minus 7 is 7. That's all wrong. Because what PEMDAS or PEMDAS or PEMDAS says is that the multiplication is more important than the addition. And that has to be done first, even when there's no brackets there. And this is multiplication. That has to be done. So even when there's no brackets there, multiplication trumps addition and subtraction. It's PEMDAS. Multiplication, division before addition, more powerful than addition and subtraction. Clearly, if there are brackets, you do that exactly first. So the answer turns out to be 3 plus 8 minus 14 minus 1. And now it doesn't really matter what order you do those in, because you're just reading right to left. So 3 plus 8 is 11, minus 14 is minus 3, minus 1 is minus 4. Okay? That's why PEMDAS and PEMDAS exists, Because otherwise people would read that series and a computer program could very easily decide, I'll do them in order. 3 plus 4 is 7, times 2 that's 14, minus 7 that's 7, times 2 that's 14, minus 1 is 13. I didn't get 13, I got minus 4. Is that okay? So that's what PEMDAS is about. Okay. The rest are just then sums, really. So if somebody said, evaluate this mess here on page 12, a squared plus b plus c over this. It may not be 12 in your note, apologies. This is on the A3 side. But a squared plus b plus c over this. Again, what you do is you go into lockdown mode. And you say a is 1, b is 3, c is 5. And you say, okay, well, a squared then would be 1 squared, plus b is 3, plus c is 5, over 2 divided by b, which is 3, minus 5. And all you do now is you respect the PEMDAS, or the PEMDAS. 1 squared is 1, plus 3 plus 5. But 3 minus 5 is done first, because it's in the brackets. So it's 2 times minus 2. Multiplication is done before the other, so 1 plus 3 plus 5, 2 times minus 2 is minus 4. Now you can do the stuff on the top if you want. You can say 1 plus 3 is 4, plus 5, that's 9 over minus 4, whatever that turns out to be, minus 2.25 or whatever. But that's why you do those PEMDASes. Okay? Okay. I'm going to move now to another topic in algebra. Not the graphical side, because that's covered in functions and graphs a lot. But I'm going to do factors. Or even, before we talk about roots, let's just do it simply as x squared minus 2x minus 8. What are the factors of that quadratic equation? Sorry? Oh, yeah, sorry. Okay. So what we do is we look at the x squared here, and we say, what are the factors of x squared? So we say x and x. And then we say the factors of 8. Well, 8 might be 8 and 1. But 8 and 1 would give us a sort of a 7 or a 9 here, which isn't great. But 4 and 2 look pretty okay. 4 and 2, particularly when one needs to be minus. I reckon that if we went from minus 4 and plus 2, we'd be sorted. Is that okay? Now, in America they call this multiplication the FOIL method. They say first, outside, inside, and last. We say let's multiply x plus 2 by x minus 4. Well, they say the first thing you do are the first ones. So that will give you x by x, which is x squared. Then the outsides, x by minus 4 is minus 4x. Then the insides, 2 by x is 2x, and 2 by minus 4 is minus 8. So if we look at that, that's our equation. But the 2x and the 4x, they're the same type of thing. They're like bananas, apples, and oranges, but they're all bananas. They're all terms in x. So we can add those up. X squared minus 4 plus 2 gives us minus 2x minus 8. And if we look at that one, and we compare it with the one on top, it's the same. So the factors we got are correct. Is that okay? X squared minus 2x minus 8. Now, some people say, well, that's okay, you spotted them, and that was okay. But you know, it's in the exam and I can't really see the factors, or they're not always as clean as that. So they give us a formula for that. We saw it in the junior certificate. And the formula says x equals minus b plus or minus b squared minus 4ac over 2a. And importantly, this works for the equation ax squared plus bx plus c equals 0. In other words, the coefficients here have to match. But we have to be very careful. The coefficients have to match as well as the sign. So that plus b is minus 2. This one here, what number goes before that x squared? There isn't a number there. But if somebody says x squared, it's 1x squared. So what we do now is we take this sidebar, and once we get the sidebar, we say, I'll get it down, and then it's mechanical after that. So a becomes 1, b becomes minus 2, and c becomes minus 8. The sign is important. And now we plug in the numbers. So we say x is equal to minus b. Minus b is minus minus 2, plus or minus b squared is minus 2 squared, minus 4 times a is 1, c is minus 8, all over 2 times a is 1. And now we go through the same very steady PEMDAS or BOMDAS or whatever and work it out. X is equal to minus minus is plus, plus or minus, 2 by 2 first is 4, minus by minus is plus, that becomes a 4. 4 times 1 is 4, times minus 8, minus 32, by minus, plus 32, all over 2. We keep going, and we say x is equal to 2 plus or minus 4 plus 32 is 36 over 2. X is equal to 2 plus or minus 6 over 2. The reason the plus or minus exists is that when you take the square root of 36, it could be plus or minus 6. And that's why we wanted that there. So let's take the first option. X is equal to 2 plus 6 over 2. X is equal to 2 minus 6 over 2. Well, 2 plus 6 is 8 over 2, which is 4. X here is 2 minus 6, which is minus 4 over 2, which is minus 2. So the answers have turned out to be x equals 4 and x equals minus 2. But we wanted something where everything was on the one side and it was equal to 0. So another way of looking at x equals 4 is that x minus 4 is 0. Because if we took the 4 to the other side. And here, we've got x plus 2 is 0. So these two become the factors. In other words, x minus 4 times x plus 2 equals 0. If we were to do the FOIL method on that again, we get x squared for that, then we 2x, then minus 4x, then minus 8 is 0. Or x squared minus 2x minus 8 is 0. And if you think about it, when this is 0, either this is 0 or this is 0. And that's the way the graph would work. But we've got our factors and we've solved it that way. So our factors are x minus 4 and x plus 2. Not because we spotted them early, not because we were good at factors, but because we used the minus b, which solved it for us, and we got them. There's a third way to get the roots as well. Let's imagine that they gave you the question x squared minus 2x minus 8 is 0. Another way of doing it is to say x squared minus 2x equals something. Probably if I took the 8 over, I'd get 8 here. Is that okay? What's half of 2? 1. So what I do is I add plus 1 there and plus 1 there. Okay? What this is actually a perfect square. This is x minus 1 by x minus 1. It's a perfect square. If you take half of this number in the middle, you get a perfect square. Is that okay? And that's equal to 9. Effectively, x minus 1 squared is equal to 9. Or x minus 1, what would you do when you squared something or square rooted it or something? X minus 1 is 3. But because it's a square root, plus or minus 3. So in other words, x minus 1 is 3, or x minus 1 is, or x minus 1 is minus 3. They're the two options that I have. Now, if x minus 1 is 3, then that would give me x is 4. If x minus 1 is minus 3, well then x is equal to minus 3 plus 1, which is minus 2. So I get x is 4, or x is minus 2, x minus 4 is 0, x plus 2 is 0. The factors are x minus 4 and x plus 2. Okay? So there's pretty well any number of tricks or bricks or whatever. When it comes to the same answer, you can get factors. Is that okay? There are loads of methods. They all end up in the same place, and that's what factors are. Is that all right? Now, what else is there on the algebra side? Well, there's one or two other things that are there, and let's see. Just look at the notes for a second. I'll cut this bit out of this section when we're recording it. Okay? But basically, in the graphic side, I used exactly the same equation. That one, y is equal to x squared minus 2x minus 8. Sorry, we were just calling it that at the moment, okay? But I decided to draw it, okay? And I called it f of x was equal to. It's the same algebraic equation. And the graph actually looks like this. It's a fairly simple graph. I've written on it, of course, from yesterday. But the graph is like this. You plug in the numbers, and you do those in the graphs, and you can look at the video for that. But what's interesting about it is that you see where it crosses the x-axis? It crosses it at 4 and at minus 2. The 2 points we were getting on the algebra side, because they were the roots. Because if you go back on the notes, we were saying that it was x minus 4 and x plus 2 equals 0, or x equals 4, or x equals minus 2. In other words, y is equal to this stuff, 4 and minus 2. But what does y equal to 0 mean? What is the y equal to 0 line? It's the x-axis, isn't it? So when the y values were 0, so effectively what you'll see is that what's done algebraically in the factors has a direct image in the visual with the same roots there. Is that okay? And we do that, and we link the two together on the graphics. The reason you want to draw these things is that, for example, above the line, you might be interested in profit. Below the line might represent loss in a business, and you'd want to minimize the actual loss. Later on, if you were to imagine that as a vase, and you were to roll a marble inside the vase, eventually it would come to a rest. It would come to a rest here when it was horizontal, where the slope was 0. It wasn't moving. Another word for the slope, anybody? dy dx, or m. M is the slope of a line. It's also the word slope. It's also dy dx. It's also tan of theta. If you have something going out here to the right, and you have to climb up a ladder or a series of steps, then you have an angle there, the opposite over the adjacent. But if there's no rise at all, and it's just the flat, well, then the angle is 0. And does anybody know how to get dy dx of that mess? What is it? 2x minus 2. And when is 2x minus 2 equal to 0? When 2x is 2. When x is 1. And when x is 1 in this graph here, dy dx is 0. The slope is 0. But we just connected. The reason I'm saying that just briefly is that I'm conscious that I'm being very purist here. I came in today to do a session on algebra. But if you look at your notes in the syllabus, it says students can answer this question algebraically, graphically, mentally, any other way they spot, any solution they see. This is the syllabus. But I've specifically chosen the same x squared minus 2x minus 8 on the algebra side that you then see on the visual. Okay? Personally, I would normally come at it to the visual first, but I want to cover the algebra because I might say just get the factors. You don't have time to draw, sorry, just get on with the algebra. Is that okay? But I just wanted to make that connection. I'll edit that bit out because when you're looking at algebra, you don't want to be doing the graphs. Is that okay? But we'll just cut that out. But I just thought, I wanted not to leave it as if it was algebra was just something out there. It's actually not. Okay. In algebra, you need to do simultaneous equations. And there are 2 types on your course. The first one is where the 2 of them are linear. I'm on page 27 of the note. 3x plus 2y is 8. And 2x minus 3y is 1. And these are two equations. What we're saying is that there are certain points, maybe just one, in this case only one, maximum of one, where these two linear equations could be the same. In other words, you could imagine that you had a graph where one line went this way and the other line went that way with different slopes. And at some point they cross. Unless they're parallel, they will cross somewhere. And this point here, A, is magic in that it's on the green line and on the blue one. So it satisfies both. We have to find out what that point is. So we do that by saying, let's make these sort of equal. So 3x, remember that an equation is a pretty straightforward thing. 3x plus 2y is 8. It's like saying 3 sliced pans and 2 pints of milk, €8. 2x minus 3y is 1. And because it's as simple as that, if you want to maneuver these, you could say, I'm going to take double that equation. If 3 sliced pans and 2 pints of milk are 8, then if I double that, everything doubles. So I'm going to take equation 1 here and double it. 6x plus 4y is 16. In the second one, I'm going to treble it. 6x minus 9y is 3. Now, why am I randomly choosing to just double or treble? I've decided that I would like the values in x to be the same. Now, I could have multiplied this by 1.5, and I would have got 3x. But multiplying this by 3 giving me 6, and this giving by 2 giving me 6, the numbers were just a bit more friendly. I can now take one equation from the other, changing the sign, minus plus minus, and I get that 13y is 13. Y is 1. Now, if y is 1, I can go back in and use that in the first equation or the second. I'm going to use it in the first one. So 3x plus 2y is 8. 3x plus 2, but I know what y is. 2 times 1 is 8. 3x plus 2 is 8. I go through all the swapping and the changing and all that. 3x is 8 minus 2, which is 6. Divide and all that, x is 2. I now have this one. So I now have both values. But because I chose the first equation, I may as well check it with the second equation. And just see if I've got it right. 2x minus 3y is 1. 2 times x, well, that's 2. Minus 3 times y, that's 1, is 1. So is that correct? 2x, 2 times 2 minus 3, well, that's 4. Minus 3 is 1. 1 is 1. It looks correct to me. Okay? So it looks like the answers are 1 and 2. Now, where do those points cross? Well, what's the definition of any point anywhere? What's the coordinates of any point anywhere? The coordinates of any point anywhere are x, y. X comes before y in the alphabet. X is the horizontal before the y. When we're reading a book, we always read across before we read down. In some cultures, they read across right to left or left to right, but they still read horizontally before they read vertically. So x is always the horizontal. I've got 2 for x and 1 for y. It's 2, 1. And at that point, 2, 1, we believe, here, it satisfies both the first equation and the second one. And visually, if we drew it, we'd see that. But we can see it without the visual. We can see it in the equations that 2, 1 satisfies the first one and the second one. Well, actually, let's do it. 3x plus 2y is 8. And 2x minus 3y is 1. Does the point 2, 1 satisfy both? Well, that's the first one. 3 times 2 plus 2 times 1 is 8. That would be 6 plus 2 is 8. That looks right to me. That point is on the first one. Now the second one, 2 times 2 minus 3 times 1 is 1. So 2, that's 4. That's 4 minus 3 is 1. 1 is 1. It's on the second one. So 2, 1 is a point on both lines. Okay? And that's simultaneous equations. The only other one they give us to do is they say, what would happen if one of the equations was linear and the other one wasn't? So they might say, solve for the following. 2x minus y is 1, and x squared minus xy is 6. Sorry, minus 6. So one of them is linear. By linear we mean that there's no x squareds. The highest power is 1. This is nonlinear because it has an x squared in it. And this looks messier. So what I'm going to do is I'm going to tidy up this bit first. I can either use the x or the y. It doesn't matter. I'm going to use the, well, I'll use the y or the x. Doesn't matter. But I'm going to put them on one side or the other. I'm going to take the y over to the other side. So I'm going to say 2x minus y equals 1 by adding in a plus y here and a plus y here. So 2x is 1 plus y. I could get rid of the 1 here if I wanted, and I could say 2x equals 1 plus y. And I could say minus 1 minus 1. So y is equal to 2x minus 1. And because that is equal to y, I could also say that's equal to 2x minus 1 there. So I have now a very simple expression. I have y on its own on the left-hand side with the value for x. Alternatively, I could have chosen to sort out x. I could have said that 2x minus y is 1. I just want x on the left-hand side. Then I'd have said 2x, get rid of the y, and I'd say 1 plus y, because if I added y here, I'd add y there. To get rid of that 2, I just divide by 2. So I could either choose to go after the x or go after the y. It doesn't matter. Is it okay? But let's imagine that I just stayed looking after the y for the moment. What was the second expression? The second expression said that x squared minus xy is minus 6. But I know that y is equal to 2x minus 1 from my table here, from the previous page. I don't like these expressions that have two variables in there. I just want to have one variable. Thanks very much. It's bad enough. But I can get rid of the y now by calling in the x's here. So I could say x squared minus x, and instead of putting in that y, I could substitute this here. So 2x minus 1 equals minus 6. So I get x squared minus 2x squared multiplying in, x by, that's plus x, is minus 6. Now I get minus x squared overall, plus x, plus 6 is naught. I could decide to change that if I wanted to x squared minus 6, minus x minus 6 is naught, just multiplying everything by minus if I wanted. But what is this anyway? This is just a standard quadratic equation. ax squared plus bx plus c is naught. Or this is ax squared plus bx plus c is naught. So, can I solve it? I can solve it for x. If I solve it for x, and I have an equation for y in terms of x, I can solve it for y. And that's as hard as it gets. That's absolutely all they can do. If they're asking you for two equations like this, they assure you that one of them will be linear and the other will be quadratic at most. Before I finish the session, I just want to let you know what's happening and what we're doing, right? In order to get to these notes, we started by looking at the syllabus on the Department of Education's website, okay? The syllabus is the official and only place that they can ask for things to be defined. What we did then is we looked at every single line in the syllabus and says what precisely are they looking for. And then for every single line, we've done a question on that line. So if they say here, for example, find the factors using the formula, find the factors through trial and error, they're all in the line. They're all in the syllabus. We've looked at every single question that's come up over the years, both before Project Maths that are continuing and through Project Maths. And we've covered on this course every single possible question form that comes up. So what we're saying here is that these question types here, when we go from the simultaneous equations that were linear to one that were linear and, that means that there's a line in the syllabus that says you need to do both. So when you look at the syllabus, you say, oh yeah, that's that, that's that, that's that, that's that. And they're all part of this course. So it's 6 minutes past 11. We'll start at 11:30. Okay? Thanks a lot. You get that?